Hey there everyone, welcome back. So in this third principle video for the chapter on fluids, we're going to talk about Bernoulli's principle, which is all about a moving fluid. Okay, so finally, fluid flow. What this means is, well, Bernoulli's principle is essentially a restatement of conservation of energy. And if you have conservation of energy, you also, in a way, have conservation of mass. Okay, so let's take a look in general here at a pipe of certain radius, and then it flares out to a larger radius. Okay, something like this. So it has some R1 and then R2. Okay, and so let's say that water goes in. Let's do it in blue here. Water goes in, right? We'll say it has some speed v1. Okay? So over a given time, we can think that there's a certain cross-sectional area of this pipe that is swept along a certain length of this pipe. Right? So over a given time, this cross-sectional area, which I'll call A1, right there, sweeps out, let's say, a distance along that pipe of length L. And so this really is a volume, which I'll call V1, right? So if you think of this fluid being an incompressible fluid, over a given time, this is sweeping out some volume of water, okay? It doesn't matter what L is, it's just, well, it's always filling up this pipe, and every instant of time, that cross-sectional area is kind of moving this way, right? So in a given time, it's sweeping out a volume. So the same thing is happening over here at the larger section. We have another cross-sectional area. This time it's much larger, but that's okay. Let's see. Let's do this. Okay. So now this cross-sectional area, I allege, has the same volume as over here. And let me show you why. So this volume over here is a length, I should say that's L1, L2, and this has a different cross-sectional area of A2, all right, such that the volume now is simply A2 times L2, okay? Now, I allege those volumes are the same, okay, based upon the conservation of mass. So let's think about it. Let's think about it here. In a given time, however time, 1 second, 5 seconds, it doesn't matter. I say that the mass has to be the same. So the mass flowing per time has to be the same at both cases. So the mass of point 1 equals the mass of point 2. If it didn't, let's take a look. If it didn't, so in other words, if this volume here, if this water were moving with the same speed in the larger section than it was in the shorter section, well, if the volumes were the same, that means the distance in between the water particles would be increasing, right? And water just simply doesn't do that on its own, okay? If you think about water going the other way, right? It's starting out in this larger section, moving at some speed, and then it hits this kind of bottleneck, literally, right? It has to speed up to maintain the same volume in that same time, right? If it didn't speed up, right, the slow speed it had here, if it had that same slow speed here, well, the density would increase. And because liquids are incompressible, that just doesn't happen, right? There'd be a literal bottleneck in the liquid. increasing the density. And that does not happen because they're incompressible. Because of that, these volumes are the same, and thus the speeds have to be different. Okay? And that allows us to say that the mass per time is the same at both points, or 1 and 2. Okay? So let's write this a little bit differently. Let's put mass in terms of density now. So the density of this fluid, right? Mass is just rho v. Take that over time. Rho v at 0.2 over time. Okay? So now we're talking about the volumes, v1 and v2. Right? I'm still saying they're the same. So now let's expand the volume out into an area, A1, times that length. Okay, and so now the areas are different, A1, that cross-sectional area, and the lengths along the pipe are different. And they are different because the volumes have to be the same. So they're trying to compensate, right, for this incompressibility of the fluid. So if the density is the same, is constant, which it is, what we get is A1, whoops. What we get is, well, before that, what is a length over time, right? Distance over time. That's equal to a speed. So what we get ultimately is the cross-sectional area for A1 times the speed at 0.1 is equal to the cross-sectional area at 0.2 times the speed at 0.2. All right, and this is known as the continuity equation. Continuity equation. It's called the continuity equation because the mass, and by mass I mean the particles of water, literally have to be conserved over a given time. And so if it's going from left to right, as the area increases, the speed has to decrease, such that the product of AV overall remains the same. All right? And again, that comes from the conservation of mass principle we started with over here. So if I were to draw now the blue speed arrow, it'd be something like that. Right? It'd be much slower. All right? So this is the continuity equation. By the way, if you wanted to, what's called the mass flow rate is just equal to rho AV, right? Right here. This is called the mass flow rate, okay? All right. So in the next video, we'll talk about fluid flow, but if they change height, right? So we'll take Pascal's principle into account a little bit, all right? So thanks for watching.